subjects, then we'll think and do. If not, we'll just put it at 8:30. Okay. And there is a problem with 8:30 on 9th, 10th and 11th. I have some program. So those 3 days, maybe we need to have a class in the evening, or we'll think what to do. Okay.
Okay.
So here, so yesterday we looked into the way to initialize values, and the impact of initializing values will avoid the vanishing and exploding gradients problem, right? And this is just a hypothetical situation we created, so that you'll understand when when the numbers are small, they'll vanish at one point in time. The numbers are big, they'll explode at one point in time. Both are a problem, depending on the, as Sishiram mentioned, right? Depending on the activation functions, or the function, the target, the output activation function, it actually may vanish or explode. Generally, for a binary class problem, sigmoid is the output function. So we may get into that vanishing and exploding gradients problem. So the next thing is mini batch. So we know the stochastic gradient descent, right? So in a neural network, you may pass 1 record or 10 records at a time, or 32 records at a time. So if you look at the neural networks I am building, I was actually sending 32 records at a time. So here we are doing it easily because the data set is in memory, right? And the whole data set we are passing it to the network at once, right? And then specifying the epochs, and then the batch size also. I forgot. I think here the batch size is also there. Let me open other file. See batch size, right? In the fit we have batch size. So if the data is already in memory, you can specify the batch size easily. But data is not in memory. Is that a situation we get into? Yes. If you have image data, right, you will not always have data in memory because the memory is not sufficient. Or if you have 1 petabyte of data, text data in your database, loading petabyte of data into memory is out of question. Whether you have a supercomputer also, you cannot save. So you will be taking data batch by batch and formatting it and passing those batches into the network. There is a way in TensorFlow. There is a data set class with which we can actually do that. Okay, we'll see that later. But the bottom line, the point I am trying to explain is we are actually passing 32 records at a time. That is batch gradient descent, if you remember. Right? Batch gradient descent. When you pass 32 records at a time, or 100 records at a time, the calculation is always going to be theta transpose x, and the matrix you are going to substitute into the activation function. Okay, theta transpose x will give you that many number of node outcomes. If you have 10 nodes, if you have, let me try to take this example. You have 4 nodes here. Suppose that you are passing 16 records here, right? Then you will get in this node you will get 16 values. In this node you will get 16 values. In this node 16. So it's going to be 4 by 16 matrix you will get, right? It's going to be for each node 16 outcomes for that particular input. For that input, right? 3 values are going in. You will get 1 output, linear combination, and then you will substitute this matrix into another activation function, and you get a matrix of output. So this whole neural network is going to be matrices only. So this whole network activity is going to be matrices only. So that's where vectorized implementation, the theta transpose x is very important. Okay, and when you look at the data, right, when we explain theta transpose x, we are considering, if you look at this, right, we are taking each row as a vector, right? That's where you take a batch, right? Each row is a column there. If you take a batch, 32 records batch, each row is a column there, right? So that's where you do theta transpose x. Rather, you have done x theta. Are you getting it? Matrix manipulation I am talking here. Getting it?
Yes, sir.
right? So that's the reason, right? When the researchers actually took theta transpose x rather than x theta, this is the reason to understand. Okay, so now you have clarity. How many weights, right? How the calculations are happening? What is batch gradient? Importance of batch gradient descent here, right? And if you look at carefully, every iteration the theta will actually get adjusted. Theta gets adjusted. Theta. So that is learning, transfer learning actually. With each batch, the learning is being transferred to the next, next batch like that. At one point, if you look at the execution also, you can see that, right? So you are getting some accuracy improving, improving, improving. Accuracy improving means the weights are getting trained. Okay. So batch gradient descent is very important, especially in deep learning. Okay, so if the size is less than 2000, right, no need of batch gradient descent. If size is more, you take batch sizes as 32, 64, 8, right, 4, 8, 16, 32, 64, like that, because yeah, because here, if you see the memory, right, in CPU, GPU, right. So why GPU? That's another question. So these matrix manipulations all happen in GPU only. Okay, not in CPU. And GPUs are pretty fast when compared to CPU calculation. The theta transpose x, the matrix manipulations happen very fast in GPU, and GPU will have memory. Okay, if you look at my GPU here, and that too NVIDIA GPU only will work. NVIDIA, yeah, yeah, NVIDIA spelling wrong, right? NVIDIA. I forgot NVIDIA spelling. Correct only. Oh, CLI. NVIDIA CLI. SMA NVIDIA. NVIDIA SMI, I think. Yes. Okay. So I forgot the command. So if you look at this, right, there is 8 GB memory in my GPU. Okay. And there is only one GPU in there. So in some GPUs, right, you'll have multiple processors. Like in CPU, you'll have multiple processors. So you can assign which processors to use for which module to execute also. Okay. So this memory is important, right? Even if you have 32 GB of RAM in your computer, right, it doesn't matter. When you are executing a deep learning model, it actually uses the GPU memory only. Getting it, right? So if your records, right, if your record size is 4 MB, and if you take 100 records, it's going to occupy 40 MB, and then if you take a batch of that, right, based on that you need to decide. Sometimes even though you have 32 GB or 64 GB of RAM in your computer, it may not work because your GPU RAM is low, right? You want to execute two huge, if you want to train two huge networks, then you should have a computer with huge GPU, right? um, so there are, it's going to be very expensive to buy, but we will not buy that. Really, 8 GB, RAM one is good enough. Okay. So that, and again, the batch size you take in 2 to the power of whatever, because these are all these are all float numbers, right? Or integer numbers, right? They'll have 2 to the power of size, right? So if you take batch size also like that, it's going to be convenient for the GPUs to get allocated. Okay, you can take other numbers also. There is no rule that you should not be taking other numbers than these batch size. You can take, but these are going to be a bit more efficient. So that's the point. Okay, and we know that learning rate decay or learning schedule in stochastic gradient descent, right? Here also we have that. In a dense layer or in a sorry, in an optimizer, you'll have learning rate decay also. What that is, a simple example equation I have taken here. There will be different equations. So here 1 by 1 plus decay rate, right, into epoch number into alpha 0. Okay, alpha 0 is the base whatever number you have chosen, and then decay rate is the t0 t1, those variables we have taken, right, those kinds of that kind of a random number, it is decay rate. Okay, so you substitute it every iteration, the alpha will reduce. What is the use of reducing alpha? The jump may be, when you are taking batch size too small, the jump may be higher, right? I don't know whether you remember this or not. When we looked into, let me show you that. So when we looked into stochastic gradient descent, SGD, right? The dot is actually jumping back and forth. See this line? It is actually jumping back and forth. So if the decay rate is same, it may get stuck somewhere here, or it may take more time to reach to the global minimum, because the jump, forward jump and backward jump are equal, right? So if you make the backward jump a little smaller, right, and that way, right, you can actually converge to the global minima very quickly. The same concept holds true here also. Okay, so and the cost function is going to be like zigzag only, because we have too many activation functions in the network. The cost function is going to be very complex. This is just on linear regression with stochastic gradient descent. But on a deep learning model with a batch size, right, it's going to be more complex. Okay, it may be a little more smoother with the batch size increasing. The curve may become smoother, right? But it's going to be complex only, like like bumpy road. Okay, bumpy road kind of thing. It may get stuck in any of these bumps or the pits. To avoid that getting stuck problem, this learning rate decay will help. Exponential learning rate decay and learning rate decay, there are two formulas I explained, but there are other new formulas are being invented most recently. And basic idea of these is to make the move quicker, learning faster. Okay, so that is learning rate decay. Any questions here?
So instead of keeping the learning rate one constant, generally we give something like 0.1 or 0.01. So with this learning rate decay, in every iteration the learning rate actually recalculates and changes.
Reduces.
Calculates
and reduces.
Okay.
A little bit reduction.
So that's the only difference, right?
Yeah, that is the only difference, and that will actually make stochastic gradient descent move faster.
Yeah.
The batch gradient descent or stochastic gradient descent. When you were passing all the data, right, at once the curve may be smoother, right, and the convergence may be faster. But in deep learning models, curve is not smoother. Whether you pass whole data or part of data, it is not going to be smoother. It's going to be zigzag only. It may get stuck at local minima. So with the stochastic gradient descent approach, it will jump around, because with each batch, right, data is changing. The pattern will change. The theta will drastically try to change. That way, it is going to come out of the pit all the time and reach to global minima and stay there. Stay there means jump around there also. We know that, right? So in the gradient descent, when it comes down, it will actually jump around, back and forth, back and forth. If you see these numbers are this line, you will understand. So it is actually moving around, right? Even after reaching to the global minima, it will actually move around. Okay. So in the internet also, there is no proof for this. We actually created this. On a data set, I created it. Okay. So that's on learning rate decay. Now we will try to understand exponentially weighted moving average, a concept which is used in time series problems. Okay, it's a mathematical concept used in time series problems. We will take this as basis to make the gradient descent learn faster. Okay, what is learning? It actually starts with some random number and then slowly moves towards the global minima, right? That jump can be made faster using this exponentially weighted moving average concept. Okay, this is a concept that helps momentum, RMS prop, and Adam algorithms a way to find out the next best theta. Okay, this concept helps us understand are the basis for momentum, RMS prop, and Adam is exponentially weighted moving average. This concept basically momentum, RMS prop, and Adam are a little bit of tweak done to gradient descent algorithm. Our gradient descent algorithms next level are the momentum, RMS prop, and Adam. Three algorithms there. They are three optimizers. We call them as. Okay. We have seen gradient descent optimizer. We have seen stochastic gradient descent optimizer. We have seen batch gradient descent optimizer. We are going to see momentum optimizer, RMS prop optimizer, and Adam optimizer. These three optimizers are the advancement of a gradient descent algorithm. The advancement is made based on this equation. Okay. First, we'll understand this equation. Okay. Exponentially weighted moving average. What is that? Suppose that there is a stock price.
Sir, 1 second, sir.
Yeah.
Sir, if we are not using the batch gradient, so will it, the algorithm takes one record at a time or all the records at a time?
If you specify
In
batch
deep
as
learning.
batch as one here,
Mhm.
if you don't specify batch size, a default value you're asking, right? I don't
Yeah,
know.
when we discussed
Don't specify hold
gradient
that
and
it will take.
stochastic,
Yeah, hold that it will take.
yeah, when we discussed gradient and stochastic, their gradient descent will take all the records. Because of that, the stochastic gradient we are using. By
But
default, stochastic gradient takes one record at a time.
yes, and
Because of that, we thought mini batch will
yes,
perform
and
better.
yes. So
So
here,
here
right,
also, yes.
we don't have gradient descent in deep learning.
Okay, it's
Starts at
STD.
STD only.
Okay.
No implementation for gradient descent either in scikit-learn or deep learning.
Okay, it's a concept we discussed.
Yeah, we should start at gradient descent and then reach to SGD. That's how you need to learn. Rather, understanding will become difficult.
So by default, the optimizer equal to SGD, then it takes one record at a time.
Yes, and or there will be maybe let us look. Maybe default size will be there. Um, maybe in the fit method we have it. Sequential fit. None they specified. None. Number of samples for gradient. If unspecified batch will be default to 32. That's a good question, Andy. We thought it's one, right? 32 it is. Okay. Got it right? Where to
Yes.
find also you got it right. So with each implementation, right, they may change. With the new versions, they may actually change this also. So it's always better to look at API. Right? And basically, our course should make you understand all these hyperparameters. Okay. Good. Any other questions?
No, sir.
Okay, good. So the exponentially weighted moving average will understand. Suppose that there is a stock market and stock prices generally get affected by the previous days, the prices, right? So suppose that this red line is one kind of model that is trying to predict the stock price, and green line is another model that is trying to predict the stock price. Okay, two models they are. Okay, so this red model and green model both were derived using this equation based on the beta value, right? The beta value is a hyperparameter which you try to put some beta value, you got red line, another beta value, you got green line. You can use this line to make predictions, right? So that's the that's the basic concept there. So what is this equation that we need to understand? So v of xt, right? So v is a function of x time, right? X time. V of xt means on a particular day what is the stock price, if it is a stock price. Okay, if it's rain, right? On a certain day what is the rainfall, amount of rainfall, like that. V is a function that actually takes the input, x value, and tries to predict the y value. Okay, v of xt can be found using beta into v of xt minus 1 plus 1 minus beta into yt, right? Yt is the time, t is the time. So if you are trying to find second days, right, v of xt, that is means second days y cap, right? Second day stock price you are trying to find, right? Then beta into v of xt minus 1, first day stock price, plus 1 minus beta into, right, second day's whatever y. Okay, so we are actually trying to predict second day's stock price, but we are using yt here, right? So second day, the outcome also we are using. So while learning, you will have that value. When you are actually building a model, right, you will have this second day's price also. You have got 100 days data. You are using that 100 days data and trying to find out this beta value that actually satisfies or that actually works correctly on your data. Got it? Did you get the concept I am explaining now? Did you get what I'm actually talking about now?
Yes, sir.
VXT is trying to find the stock price at a teeth day, second day. But in the equation, we are using second day's stock price also. How can I do that? Right? While training, right, you will have that. No, while predicting, you will not have it. Right? So if you have to find out the first day stock price, right, it's going to be x0, right? There is no value, so you take v of x0 is equal to 0. So now let us try to take beta is equal to 0.9 and try to see what happens here. Okay, if we try to understand relationship between days and stock price for a different beta value, we'll be able to capture different patterns. Okay, we'll be able to capture different patterns. To understand pattern, you can use this equation. So here I have taken beta is equal to 0.9. When I try to find the first day's stock price, 0.9 beta into 0th day's prediction plus 1 minus beta into first day's stock price, actual stock price. So 0.9 into 0, because v of x0 is going to be 0, and then 0.1 into y1. So it's going to be 0.1 into y1. So no, first day stock price I predicted. What I'm saying is 10% of the first day's actual price. Okay. When I took 0.9 as beta, I am saying the first day stock price is equal to 10% of the actual first day stock price. Let us look at the second day. 0.9 into v of x1, right, plus 1 minus y into v2, y2. So I am actually taking the prediction into consideration, first day's prediction into consideration to make the second day's prediction. Okay. So 0.9 into 0.1 into y1 plus 0.1 into y2. Again, I am taking second day's 10% only. But first day's 0.09 is 9%, right? First day is 9% plus second day is 10% I am considering in predicting the second day, right? Third day I am going to take, first, third day is 10%, second day is 9%, and first day is maybe 0.8% or something like that, 0.81%, right? So when I am predicting teeth day stock price, I am considering all previous days predictions. Right? Previous days actual values. Okay. Along with the current days whatever also. Right. Got it? Let me look at this equation once. Maybe this is y t minus 1. Y t minus 1, 0, y 0 will not be there, right? So y t only. Sorry. Y t only. Let me look at it. Yeah, Vt is equal to beta into Vt minus 1 plus 1 minus beta into theta t. I think, give me 1 second. Yeah, xt, right? This is yt. That's like, so equation is correct only. Equation is correct only. Okay. So, we are actually considering, a little bit of previous, little bit of previous, little bit of previous, and 10% of the current one when beta is equal to 0.9. So when you look at this equation, right, for 10 iterations, the prediction is not going to be correct. Because, if you see the first one, right, only 10% of y1 it is taking. Second one, 9% of the y1 and 10% of the y2. But it is considering the previous values. Till 10 iterations, it is not going to be correct. From that point onwards, the actual value and the predicted value are going to be close to each other. Okay, depending on beta. Okay, if you change beta is equal to 0.1, right? So beta is equal to 0.9. We'll consider previous 10 days. Previous 10 days actual value to calculate the current days predict current days price. If beta is equal to 0.1, right, it will consider only 1.1 day, yesterday and day before yesterday is only 10%. It will consider. If it is 0.99, right, it's going to be 1 by 1 minus beta. It's going to be more 100 days. It's going to consider. Okay, so if you change this beta, you can identify that how many previous days is affecting current day stock price. Okay, how many previous days is affecting current day stock price. That is the exponentially weighted moving average formula and the concept. Any questions here? Any questions here? So this equation is going to help you because what we are going to do is in this v xt minus 1 and yt, we are going to put gradient descent, previous gradient descent and current gradient descent, something like that here. That way we try to predict the current gradient descent. So in our stochastic gradient descent, it is jumping around, right? If we understand this jumping around pattern, instead of jumping around, you can predict in the next, next. Instead of moving smoothly like that, if you know the pattern, you can actually jump, right, like that. So we are actually trying to create that situation using the exponentially weighted moving average. We'll understand pattern and then use that equation to jump around. Got it? Got it? That is momentum. Any questions here? Any questions?
Last two statements, sir. I was actually thinking if the beta value is more, it takes less days of data to predict the.
This is the formula. 1 by 1 minus beta days it will consider. 1 by 1 minus beta t's it will consider. Time steps.
So how this beta equal to 0.1 will take only 1.1 days of data.
See, if you substitute that into this one, right, you will get to understand. If you put beta is equal to 1.1 here, 0.1 here, let us try to draw that and see. Write it. Give me 1 second. So here, right, I took 0.9. Only 3 iteration I did. If I have done 10 iterations, right, it would have been more clear. But you asked 0.1, right? That's a good question. So let me take a white sheet. That's better. Here. So 0.1 we should take, right? V of x1 is equal to V of x1 is equal to 0.1 into Vx0 plus 1 minus beta 1 minus beta means 0.9 0.1 1 minus 0.1 into yt, that means y1. Okay. So what is y1 here? No value there, right? But no, this is going to be 0, right? Point v x0 is 0, so it's going to be 0.9 into y1. What it did, current day 90% it took. Okay, v of x2 is equal to 0.1 into v x1 plus 1 minus 0.1 into y1 y2. This is y2. It's going to be 0.1 into v of x1 is 0.9 into y1 plus 0.9 into y2, right? V of x3, if you do x3, that's enough. So you'll understand what's happening there. X2 plus 1 minus 0.1 into y3. Right? So here 0.1 into, what is y2? 0.1 into 0.9 into y1 plus 0.9 into y2. Right? This is all in one bracket. Right? Plus 0.9 into y3. If you look at this, right, this one is like 0.09, right, plus y1 plus 0.9 into y2. So current day 90%, previous day 9%, 99% it is actually taking. It is taking from only 1.1. That's what 1.1 day. That's what, like 99% of the value is coming from current day and previous day only, right? Got it?
Yes, sir, that's right.
So here also 0.9 is taken. 90% is taken from current day. When you multiply this whole thing, right, it will become like this. 0.1 into 0.1 is 0.01 into 0.9 is going to be 0.9, right? 0.0009 into y1 plus 0.09 into y2 plus 9 into y3, right? Plus 0.9 into y3. See, 90% is taken here, 9% is taken here. 99% again from the current day and previous day. If you calculate y3 or y4 also, it's going to be like this only, like that only. Y4 it will take 90% and Y3 it will take 9%. Right?
Yes, yes.
Yeah. So this formula actually works. 1 by 1 minus beta actually works. Okay. So this bias correction is one concept we'll talk in normal batch normalization. So there this is going to be useful. So that's where I kept this one and this concept also. I'll talk about that, when I'll come back and talk about it again. So let us look at momentum, one concept today, and stop there. Okay. So in momentum, right, we are not going to calculate derivative directly. We are going to calculate V of derivative. Here X is the derivative. Okay. Beta into V1 into the previous derivative, previous gradient, plus 1 minus V1 into current gradient. Right. In this equation, you have current Y value and the previous, whatever predicted Y value you have, right? So this equation is very suitable for our purpose. So instead of calculating derivative directly, we are using this. That means we are trying to understand this kind of a pattern in that gradient movement. If you know the pattern in the gradient movement, your prediction is going to be more accurate, or the jump is going to be more accurate, right? Instead of I think here it is. Instead of moving, systematically, you are understanding pattern and then jumping. You are not going to move anymore. Generally you are moving carefully, right? Once after, maybe if you take 0.9 as the beta, first 10 iterations it may go a little here and there, right? But from 11th onwards, right, it will make jump, jump. Maybe in 4 steps it will reach to the global minimum. Got it? Understood the concept? How momentum algorithm is working? Any questions? In general, normal gradient descent or stochastic gradient descent algorithm, it is W is equal to W minus alpha into derivative of the cost function with respect to weight, W. But here, a function of derivative of cost function with respect to W. And that function is nothing but a exponentially weighted moving average function. Got it? Depending on the beta, the pattern recognition is going to be very accurate, and then it will move faster. If beta is chosen properly, the theta finding will be faster. If beta is not chosen properly, theta finding is going to be slower. Got it?
So in gradient descent, we will take the derivative of the cost function, right?
Mm.
So here, what is the difference, sir? V of
It is a function of derivative of cost function. The function is nothing but the exponentially weighted moving average function.
what is that function, sir?
Exponentially weighted moving average function. This function only. Beta.
Exponentially weighted moving average.
In xt, right? In the place of xt and yt, we kept derivative. See that? At current derivative, current gradient, we are not generally what is the value used here? This is the value used, right? dj by dw we are using in normal gradient descent, right?
Yes.
But here we are using v of derivative. That v function is derived. So we are not directly using the slope of the tangent for the cost function. We are actually finding the pattern. We are trying to understand the pattern by changing this beta, right? If you understand pattern, what will happen? You can actually predict the derivative. Maybe the derivative after 5 steps, and move to that place. You actually can move this W to that place instead of moving slowly from here to here to here to here. You can actually jump. That jump is going to be made using this formula, because you already understood that certain beta is actually jumping faster. There is a hyperparameter. You can play with that and make the algorithm reach to global minima faster.
Okay. So based on the beta value is directly proportional to the jump.
Based we shouldn't be saying directly proportional there. Depending on the cost functions curve, you should choose beta.
Okay.
Right here, if you see, if you choose 0.1, this pattern is not recognized properly. Right? If you use that beta, convergence is going to be slow. Right? Maybe I should take another example like this. Maybe let me take another. Suppose that your cost function is like this. Okay, and another cost function is like this. Right? For this, right, beta is equal to 0.8 may work. For this, beta is equal to 0.9 may work. Right? When you are understanding the pattern properly, how the gradient is moving, that's you are trying to understand how the gradient is moving in the initial stages. Using that movement, you are actually trying to predict a value that is far. You have here, you are here, you are here, you are here, you are here. By this time, you understood the pattern, so you are jumping right directly here, right? Again jumping directly here, again jumping directly here, like that. Pattern recognition is applied while finding gradients also in the advanced algorithms.
Yeah, got it, sir. So we will it move, ahead even after the global minimum if these jumps are bigger?
No, that again comes down to that derivative of the cost function, right? So that derivative will become 0 here. Right? When you look at the equation here, right, this will become 0. Right, this will become 0, and this term will become 0, and kind of this will also become close to 0. This whole term will become close to 0. Then v of whole thing will become 0, and w will not move. Got it? The previous derivative and the current derivative will also be close to 0 when the theta move reaches to the global minima, right?
Yes.
So RMS prop and ADAM are just more complex versions of this same concept. Exponentially weighted moving average is the concept we need to understand here. Okay, I'll stop here. I think Narayan joined. Okay. Good. I'll stop here.